Ask My Instructor 8.5.27. Use a table of integrals to evaluate the following indefinite integral. This integral requires preliminary work such as completing the square or changing variables before it can be found in a table. I start off by observing that we have sine x multiple times in the denominator and cosine x once in the numerator. And this makes me recall the fact that the derivative of sine x is cosine x. And it seems a substitution of u equals sine x would make sense. If I do a substitution of u equals sine x, then du equals cosine x dx. And the integral becomes this. At this point, I would probably use partial fractions to finish the problem, but the instructions say to use a table of integrals, and so I will proceed in that direction, although I have to tell you, I do that rather reluctantly. We do need to keep track of the substitution that we made. Since I am not allowed to use my own idea of partial fractions, which I did think was a good idea, I will use the given idea of completing the square. Let's look in the denominator. To complete the square, it's easier if the coefficient in front of u squared, if that coefficient was 1. So what I do is I pull out a 6. And when I do that, inside of my parentheses, the coefficient in front of u squared, that coefficient is now 1. And I'm only talking inside the parentheses. So now, inside the parentheses, I look at the coefficient of the linear term. I take that linear coefficient, I divide it by 2, and square the result. What I get is a value of 7 over 12 quantity squared. And what I want to do is add and subtract that value. Once I've done that, I've done what we call completing the square, and I've done that inside the parentheses. Looking inside the parentheses, the first 3 terms make up a perfect square. So I'm going to write those first 3 terms as a perfect square, and this is what I get. Now that I've done this labor, I'm now going to put what I have found into my integral. I have to put it in the denominator. When I do that, I get a rather ugly looking fellow. I will pull out the 1 over 6. But still, my fellow is rather ugly and unwieldy, and in order to clean it up a little bit, I'm going to do another substitution. The substitution is w equals u plus 7 over 12. If I make that substitution, then dw equals du. And my integral becomes this. All right. The only problem with doing this is that my list of things to keep track of has grown. So do look up in the right-hand corner. We do need to keep track of all these changes we have made. But on the other hand, we are ready to look at a table of integrals. So let's do that. My integral is dw over w squared minus a squared. I'm ignoring the 1 over 6. That's really not important right now. I do need to keep track of it, but for integrating purposes, not important. So just look at the pattern. I have dw over w squared minus a squared. I'm looking for that in a table. This table this piece of the table came from the back of your book, and I just cut out the piece that I'm interested in. I'm looking at integrals involving variable squared minus number squared. And so let's go ahead and see which one looks most like ours. And that would be number 64. That has the closest link. What a table of integrals does is it finds antiderivatives. It integrates for you. But as you know, you have to do the footwork to make your problem look like one of the given antiderivatives in their table. And that was a lot of work in this case. But now that we have done the work, we're ready to use the formula. Just keep in mind that instead of x, we'll be using w, and also keep in mind that we can't drop that 1 over 6. So using the formula, I get that my integral is equal to 1 over 6 times 1 over 2a ln of w minus a over w plus a. All of that plus c. And now that we have the integral done, it's time to unravel using substitutions. I'm going to work backwards, and I'm just going to look at the quotient w minus a over w plus a. Instead of w, I'm going to put in u plus 7 over 12. Instead of a, I'm going to put in 7 over 12. Next, look at my numerator. I can do that subtraction. I'm going to get 0. In the denominator, I can do that addition. I'm going to get twice of 7 over 12, which, as you know, is 7 over 6. To clean this up further, I multiply the top and the bottom by 6. I have to do this step carefully, but this is what I get. We still have some unwinding to do. Instead of the u, I'm going to put in sine x. So I'm going to rewrite this using sine x instead of u. And this is what I get. Recall, what I have found is that little piece inside of the absolute value. So instead of w minus a over w plus a, I'm going to put in 6 sine x over 6 sine x plus 7. Make that change. And the only other thing I need to do is I still have that number a. I haven't made that switch yet. So notice that I have 1 over 6 times 1 over 2a. Well, what is that? I'm having a hold the value 7 over 12. Let's figure out what 1 over 6 times 1 over 2a is equal to. 1 over a, if a is equal to 7 over 12, then 1 over a is 12 over 7. And when the dust settles, I get 1/7. Down on the last line is my final answer. So I'm ready to go look at the choices given me by my math lab. This particular problem was a multiple choice question. It doesn't look like mine is any of the ones given, and perhaps I got the problem wrong. But hold the phone. Let's look at possibility B. See how B has that negative out in front? If I were to bring that negative into the log, what that would do is flip the fraction inside of the log. And if you if you do that, if you bring in the negative, meaning you're using the reciprocal of the fraction, if you do that, you get my answer, which I think is a little prettier, don't you? I don't know where they got theirs. Perhaps they used a different table, or perhaps they cheated and used partial fractions, which was rather nasty of them since they made us use partial fractions. They made us use the table instead of partial fractions. All right, well, we got the problem done anyhow. and have a great day.